Okay, so we are now recording. So let me hand things over to group 12 for their MEC 2 capstone presentation.
I think Elijah is going to start us off.
Oh, and we are not hearing sound from Elijah.
Hello.
Oh, there we go. Okay, success.
Okay, you guys got me? Okay, so sorry about that. I was working just a second ago. Okay, so good afternoon. Thank you guys so much for taking some time out of your busy schedules and coming reviewing our design for us, giving us some pointers and your insight. So we are Project Accelerate. We are student group 12 of EML4501, section 13068. We're going to go ahead and just jump right into it with a quick introduction about our group members. So we'll go ahead and go to the next slide.
Hello, my name is Jason. I'm a fourth year UF mechanical engineering student. I've been heavily involved in the formula team here. This year I'm serving as chassis, or last year I served as chassis lead. This year I'm serving as chief engineer.
Hello, my name is Joshua Kempfert. I'm also a senior mechanical engineering student with a mathematics minor. I mainly participate in undergraduate research in computational material science, and I'm planning to enter graduate school and get a PhD.
Hello, my name is Snell Mizra. I'm also a fourth year mechanical engineering student with a minor in business administration. I am also currently a thermal design lab TA.
So hello, I'm Elijah Schott. I am a third year mechanical engineering student. I also have a computer science engineering minor, and I'm a UF design and manufacturing lab teaching assistant.
And finally, hi, I'm Brianna Smansky. I'm a fourth year mechanical engineering student as well. And I've interned with Lockheed Martin for the past 2 summers with missiles and fire control. I've also been a statics TA for 2 semesters, and I'm currently working in a research lab as well. So we just wanted to outline our presentation really quick and what we're going to talk about. So first, we're going to talk about the Hedgehog concept that we came up with for our design. Then we're going to talk just about this whole system in general, and then the subsystems, highlight some key features, go over some cost summaries, and basically explain why we think you should choose our project to be manufactured in MEC 3. So to start, our Hedgehog concept was basically built around a worry-free launch system. So we realized that the customer puts a lot of time and energy into making their product. So we wanted to make the whole mission process of sending their product up into space. We wanted to make that worry-free, specifically with the launch experience. So a lot of our design features focus on reducing the loads on the CubeSat itself while it is being launched out. This happens with using constant force springs. Vertical loading installation can also happen as well, which we'll explain more in detail later. And then we also have Teflon coated rails and a magnetic power connection that reduces friction as the CubeSat is disengaging out of the CSD as well. So those are just some highlighted features, and Jason's going to talk about a little bit of an overview now.
Yeah, so a quick overview of our CSD. Our CSD houses a 12U CubeSat, utilizes a custom power and communication system to connect to ground, and also has our unique worry-free loading and launch mechanism. Right now, the overall mass of the system is just about 5 kilograms, a little bit under that. So our housing, like I said, fits a 12U CubeSat. It's comprised of 5 steel plates of 775 T6 aluminum. The housing's overall mass is about 2.5 kilograms, about half the mass of the entire CSD, and also accounts for liftoff and descent venting to ensure that there aren't any extreme pressure differentials that can damage the CubeSat during launch. Like I mentioned, we chose 775 T6 aluminum for our housing. Mostly for its high specific strength. 775 is one of the highest publicly available alloys of aluminum. But when putting that next to other metals like titanium, magnesium, its cost is very, very low. And when putting that next to other materials with high specific properties like composites, carbon fiber, The manufacturing machinability is huge. It's so much simpler. Additionally, aluminum is electrically and thermally conductive, so we can ground all of our electronics to it. And aluminum is corrosion resistant and has low outgassing. As far as manufacturing goes, aluminum is very machinable. The way we intend to make our housing is by pocketing out plate stock of aluminum. This is low cost and easy to obtain. And we're going to pocket all of this out on a 3-axis CNC milling machine. Basically, what this does is allows us to cut our part count way down. So like I said, the entire housing is only 5 parts, 4 unique parts. And with that, we have fewer joints and connections, which are fewer potential points of failure. And again, since it's made on a CNC machine, we have high precision parts, which is very important for our launch mechanism. Additionally, it's easily adaptable to fit different mount designs for different launch vehicles or applications. So we did a quick wall thickness analysis to try to figure out what the minimum thickness of 775 wall we needed in order for our housing to withstand all of the structural loads primarily seen during launch and liftoff. So we chose a factor safety of 1.6 for this. And by doing that, we found that our minimum wall thickness is about 1 millimeter.
Moving on to the mounting configuration, we actually employ somewhat of a unique system in that instead of hard mounting to the launch vehicle placed through bolts alone, we actually employ 2 silicon rubber shock isolators. And so what that allows you to do is that the shock can be applied and it isn't the aggressive shock loads during jettison aren't going to be transmitted directly to the CSD. This also changes the natural frequency of the structure, so we achieve about 300 hertz, which is above the mandated 120 hertz. And so it reduces our maximum predicted shock load from 4,000 G to 600 G, and we'll show evidence in a minute for that. And we utilize most of our extra mass here. So we use about 1.46 kilograms total. And so how we actually accomplish this is that NASA's Space Launch System provides a shock response spectrum at the payload adapter plates. And so what this provides is it provides the peak shock acceleration for a hypothetical single degree of freedom system with that frequency. So as you can see here, if we lower our natural frequency, we will lower the effective shock load on the CSD and on the CubeSats, which is great. But we also have that 120 hertz limitation. And so also the effect of having these rubber isolators, as you can see here, is it makes the system behave as if it was a single degree mass spring system. So how we design these isolators is as a factor of safety, we design them to survive a sustained worst case scenario of 4,000 G shock. So we calculated the required area, assuming conservative silicon material properties. What we found through our derivations was that we lower our natural frequency to reduce shock, but it always increases the mass essentially, and there's a strong diminishing return here, as you can see in this plot, where to lower the shock under 600 Gs, you have your isolator mass creep up, and we're limited to 5 kilograms total. So we selected a reasonable 0.68 kilograms of silicon rubber total, and that gives us a shock load of 600 Gs and a natural frequency of 300 hertz. So ultimately, the reason why we used an elastomer for this purpose is first, they have high loss coefficients, as you can see here on this Ashby plot, and that's valuable for dissipating energy quickly, so you're not having a vibration that builds and resonates. And also they have low elastic moduli. And if you recall the relation on the last slide, the mass required for the rubber is actually proportional to the elastic modulus. So it's very valuable to choose a material with a low elastic modulus. We chose silicon rubber specifically because it has a great track record in space applications, depending on the grade. It can be made to be low outgassing with a wide operating temperature, and also it has a high compressive strength among elastomers, and which is important because actually we're only loading the elastomer shock isolators in compression. We're not loading them in tension. And so for performance requirements, we showed, like we calculated, we need an area of 523 centimeters squared minimum. So we chose that in a 6 millimeter thickness. We actually distributed this across the entire bottom surface of the CNC for the even shock load. But so how we actually did this, that area is not equal to 523 centimeters squared. So we actually cut out holes to match our performance metric. For prototyping, we would probably just punch these out or cut it. The tolerance doesn't need to be great. But for production, we would likely mold this to save some material waste.
Next, we're going to talk about the door mechanism. So for our door, we are using torsion springs to open the door and a separation nut actuator, which holds the door in place until it is ready to open. We are using a 270-degree torsion spring, but we are only using 180 degrees of that range. And the total mass of this subsystem came out to be about 0.339 kilograms, with 0.234 kilograms accounting for the aluminum plate for the door, and 0.057 kilograms accounting for the release actuator, and some of the other small miscellaneous stuff accounting for the rest of the mass. We ran some calculations, and according to our calculations, the time to open the door a full 180 degrees was 0.18 seconds. And for the door mechanism, the torsion spring, actually, the spring is loaded in the case when the door is closed, and once the separation nut is released, that's when the spring returns to its natural state, flinging the door open. The material selection for this section, we used the same material as the outer housing for the door, which is the 7075 aluminum, because of the same properties, the high specific strength, the machinability, and the low cost. For the torsion spring, we used 304 stainless steel. And when the door opens, it bumps against a silicone rubber pad, which absorbs the energy from the door opening, which we will expand on later. And we are using a space grade separation nut actuator, which is both mechanically and electrically redundant, with 6 kilonewtons of preload, and uses an M5 thread hole. The space actuator is sourced from Space Lock, so we know that it works in space. For manufacturing, the door and the hinge are both going to be CNC machined, while the rest of the components listed are OTS parts. And for the tabs holding together the torsion spring, as you can see in this picture, will be welded on.
So there are a number of computations that we perform to ensure that the door functions properly. First of all, with the release, what we actually accomplish here is we have the bolt slide out, and you can see there's a little hole, like tab on the door, which engages with the bolt. As the bolt slides out, the door slips through it. So an important consideration with this is ensuring that we have a long enough bolt to allow this freedom of travel. As you can see here, through some basic geometry, we calculated the minimum bolt length, or minimum travel length rather, as 6.85 centimeters. But for a factor of safety, we chose a bolt with travel of 8 centimeters. And so another consideration is that the CubeSat is actually pressed up on the door prior to release by the constant force springs. But as the CubeSat launches, we felt it was imperative that the CubeSat not keep in contact with the door, mainly because there's friction and collisions happening that would make it a very unpredictable load path. So what we actually just do here is that we design this door such that it would swing fast enough that it never contacts the CubeSat after it initially breaks away from it. So as you can see here, we get our position of the CubeSat and the position of the edge of the door that would contact the CubeSat. And we form some governing equations here for that. What we can see from these equations is that actually lowering the height of the hinge is beneficial in terms that the door does not need to rotate as fast to avoid the CubeSat in that case. So that's the reason why our hinge is actually somewhat offset on the bottom of the model. So moving on here in analysis, we numerically defines essentially the minimum strength torsion springs that would allow the door to rotate out of the way to a good factor of safety. So what this actually translates to is a torsion spring constant of about 2.07 pound force inches per radian. At maximum deflection, when the door is at its top position, this would be about 6.5 pound force inches of torque. But if you were to manually close the door yourself through the lever arm, that would only require 1.2 pound forces. And so when you actually look at our dynamics plots here, you can see that both the door and the CubeSat start at a position of 0 and from rest. But as you can see, the door immediately separates with a much higher acceleration than the CubeSats. And so they break away almost instantly, meaning there will not be contact. So another important consideration is that as the door comes down and reaches its range of motion, we can expect it to bounce back and rebound. And we wanted to ensure that it would not re-collide essentially with the CubeSats to avoid losses and unpredictability. So what we actually ended up doing here was putting a silicone rubber pad at the bottom to contact this portion of the door and dissipate some of the kinetic energy through hysteretic damping. So assuming a reasonable elastomer loss coefficient of about 80%, we calculated the rebound, and we get that the door would go to an angle of negative 9.6 degrees. And so that basically the danger zone where it would contact the door is 6.4 degrees. So we have a good factor of safety here. And to the right here, you can visualize the door motion as it bounces up and down and loses its energy. But that said, we still recommend testing to validate these calculations.
Okay, so now I'm going to talk about the launch mechanism. So after the door opens, the CubeSat, like Josh said, is pressed against the door. So immediately when the door opens, it's launched out by constant force. The CubeSat to launch out. The constant force springs are on spools and the mounts, again, as I've shown right here. And we also have Teflon coated rails to provide really low friction because like we said, we wanted the launch to be really smooth and not have any disengagement or a lot of friction, slow down the customer needs that they asked for, because there were specific acceleration and velocity properties that they wanted us to make sure that we could handle. We also have a vertical CubeSat installation procedure that's actually pretty cool. So the constant force springs each take about, I think it's 14 to 15 pounds. So since we have two, they have about 30-pound forces. And our CubeSat weighs approximately 45 pounds. So when you're installing it, the weight of the CubeSat is going to get the potential energy of the springs and, force them back in the launch plate, and gravity is going to hold it down. So you won't have any kickback from the springs. But when you go into space, there's no gravity. So the springs actually have a greater force than the CubeSat, so they can propel them out. So we thought that was a really cool feature. We also wanted to talk about why we chose constant force springs versus linear springs. So as you can see on the math on the PowerPoint, basically shows you that constant force springs produce less force than linear springs. They actually produce half the maximum force, which is required. So they all around just do better work for what we wanted for this design. I said we had two about 15-pound springs. And also when you load them in, they don't take up a lot of space inside the CSD at all. As you can see in this picture right here, the thickness is very small. So we thought that was another good feature to use the constant force springs. Really quickly going through material selection, the launch plate and spool mount. So this is the launch plate right here. Spool mounts, they're both made out of different aluminum alloys due to their high specific strength and easy machinability. Our constant force springs are made of stainless steel, basically because we wanted them to be really corrosion resistant and have a high strength. And then the spools that the springs rotate about are made of Teflon, again, for low friction purposes. To manufacture the launch plate, so this is our launch plate right here, we would first water jet the main profile to get this geometry that we want. And then we would CNC the faces that go against those rails to finish up that process. Our springs are off-the-shelf parts. And then these mounts right here, we would also machine those using CNC machining. The spools are right here, and we designed them to intend them to be allowed to be 3D printed. You could also do injection molding, but that might be a higher cost. So I think we decided we want to do 3D printing if we were to do it, but you can do either or. And then an analysis that we did was the exit velocity analysis. So one of our customer needs was that the exit velocity needed to be between 0.5 and 2 meters per second. So we just did an energy balance equation for our math, as you can see right here. The highest energy loss that we considered was from the spool turning and the friction. I think that accounted for about 5% of the energy loss, which was the most in comparison to everything else. And then after we did all the math, this was the final equation that we got, which associates to this graph. And so basically, something I forgot to mention is that you can position, I'll go back. Right here, we have bolts. So they basically block the launch plate from going to a certain distance. So let's say you wanted to put the bolt here, the launch plate would only launch here. And this provides adjustable velocity features for the thing. So if you want it to be between 0.5 and 2, you would have to put the bolt between 2 centimeters and approximately 32 centimeters to meet the customer needs. So it's very variable.
All right, I'm going to go over the communications and connection subsystem here. So our communications and connection subsystem receives 28-volt DC power from the launch vehicle. That's a given from our customer needs. So we are going to equip it with a microprocessor and an X-band radio transmitter that can receive commands from Earth to actually release the door actuator and launch the CubeSat. And then it also provides power to the CubeSat continuously up until the moment of launch through a magnetic connection. And that magnetic connection kind of just ensures that through any sort of bumps or vibrations in the launch, it stays engaged and that the power is continuously provided to the CubeSat. All right, so for component selection, the communications and connections subsystem has a lot of off-the-shelf parts, but it's still important to look into the componentry here. And there are some differences between a prototype model or an actual production model. So for the prototype here, we've got our actual housing that's going to encase all of our electronics here. It's a 6061 T6 aluminum alloy 16 gauge sheet housing. And we chose this just because it has low density, so it doesn't take up too much weight. It's affordable, it's easy to manufacture, and it's relatively strong for that weight. Then we have our Raspberry Pi Zero microprocessor. We chose this because it's very small, it's affordable, and it operates on 5 volts. And these are actually space grade, which I didn't know, but people often send them up into CubeSats or even low Earth orbit CubeSats as the main processor of their whole system. So, but of course, as you see there, the Raspberry Pi Zero operates on 5 volts, and so does our door actuator. So we're going to need some DC to DC step-down converters. We have 2 of them there. One of them is going to convert that 28 volts down to 5 volts. That's going to power our microprocessor and our door actuator. And the other one is going to step down to 14.4 volts, and that's going to be for direct power supply to the CubeSat. That's the number that our joined Aero group gave us, is what their CubeSat needs. Now for a production model, there's a few things you probably want to change, and for the sake of reliability and making sure everything is good to be set into space. So we'd probably replace our transmitter. We have a very cheap transmitter in our prototype, but we'd replace our transmitter and our DC to DC converters with actual space grade components. Unfortunately, I've tried to contact these companies. They are a little bit rough to give me any sort of specifics on them because they are very expensive and they're very proprietary. But the housing and the microprocessor can stay relatively unchanged. Those can be the same in a production model. And a really important step in this process is if we're going to go through a full production, we'd want to consult with an electrical engineering firm or just an electrical engineer, bring them onto the team just to make sure that we're safe and we're doing everything up to the proper code. All right, so for the manufacturing and assembly, so the communications box itself, which is that aluminum 6061 T6 sheet, the geometry and the grommet holes of that can be cut by a CNC water jet. The communications box is probably going to be bonded to the housing with Loctite high sol epoxy, along with the magnetic connector that can be bonded to the launch plate with that same epoxy. All other components are going to go within that communications box and they're off the shelf. But the reason we chose this epoxy, it has a high thermal resistance, low shrinkage, and it's pretty good with different environments. If there's any sort of moisture or humidity, it's a good option for that. So, all right. So next, obviously, even if we have a pretty low force magnet, it's going to basically impart some sort of force onto our launch or to the CubeSat during launch. So we wanted to try to figure out how to account for that. So there's identical ring magnets that are both on the CSD and the CubeSat that interact and connect. And the off-the-shelf maximum force is about 0.4 pound force. And so because of this, when we have two magnets interacting, the magnetic force between magnets is it drops exponentially as they move further apart. So we can actually kind of describe this relationship. We graphed it in the next slide here. So basically up until that moment of launch, it's going to be at its maximum magnetic force because those two magnets are going to be in contact. Once that plate separates from the CubeSat, that magnetic force is going to drop down exponentially pretty fast. We've graphed this here to show the relation and the break point. And using this relation, we can kind of correct our previous launch energy balance equations and find that the force that this magnetic attraction exerts on the deployed CubeSat is pretty much negligible. I would love to do some more testing with it too if we're going to go into a full production though. Okay, next up, we're just going to kind of summarize some of the design highlights and key features. So first off, for that housing system, it's very low weight for a housing system, just 2.41 kilograms. It's got a very small footprint because of those external constant force springs, only 26 by 40 centimeters. And it has holes that allow for that ascent venting, making sure there's no pressure differentials. For communications and connections, we use an X-band radio transmission system to communicate to Earth. And we have a magnetic connector to ensure that the CubeSat gets continuous power and that the connection is not broken. For the launch system, we have a constant force springs doing the heavy lifting, and we have a adjustable exit velocity with the sliding bolts there, and then a 0.66 gram launch acceleration, which is really nice because it's a lot lower than if you were to use other spring systems. Our door system uses a space grade release actuator, and the door opens to 180 degrees in just 0.18 seconds. And then our mounting system takes advantage of silicon rubber mounting pads to reduce maximum shock loads down to 600 Gs. And in our next slide here, you can see this is just the door open. During its opening process, the CubeSat gets expelled, and you'll see as the launch plate moves up here, I've just exploded out the magnetic connector so you guys can see a little more clearly. And then you see that the actuator bolt has a pin through it, which gets caught in that little tab there, and that ensures that we don't shoot debris out into outer space.
Next, we're just going to quickly go over some costs for the prototype. Our raw material cost for the prototype was about $391. And then we have a breakdown of our labor costs for one prototype, with most of the time spent on assembly and fabrication, with the total incurred labor costs being about $3,000. Next, we ran a quick energy calculation for the energy cost, assuming the average energy consumption for a commercial building. And we assumed that our manufacturing building would have a square footage of 580 square feet. And with this gave us a monthly energy consumption along with our monthly energy demand, resulting in our total monthly energy costs about 1,500. And this brings our total cost of the prototype to about $4,932. And this cost is above the 500. This cost is higher than the 500 because the 500 accounts for the raw materials, and this accounts for both the energy and the labor costs. Next, we have our production cost of a full scale 100 unit production run of the prototype, with the material costs being 39,000 and the labor costs increasing due to the number of hours needed, number of hours and workers needed for producing the 100 units of the prototype, which brings our labor cost to about 300,000. The same calculation was done for our energy costs, and this energy costs increases to about 146,000, which brings our total incurred cost to about $485,301, which is under our 500K budget. Along with this, we ran a quick calculation for our for a cost of a full product, and we found that it would be about 40,000, and this includes both the space grade actuator and the X-band radio transmitter, which were quite expensive. And we decided to sell our product at about a 30 to 40% markup, which brought the total selling price to about 70 to 75,000. And for this cost, we would still need to do some market research to determine if this price is either too low or too high compared to other products on the market.
Just want to say, I saw your chat. This is our last slide. But we just want to go over why you should choose Project Accelerate to manufacture for next semester's Mech 3 class. So just a couple of key points. We use constant force springs. They're very easy to get because you just have to buy them off the shelf. Most of our parts are made out of aluminum, so they're very readily machinable and cost efficient. Our vertical loading system allows for the prototype to be installed easily. You can also test out geometry features to make sure the CubeSat can in fact fit in. So the dimensioning and tolerancing is all good. It's very compact, so you can store it easily again, and the prototype cost was very efficient as well. And we just wanted to wrap up and say thank you to everyone who's listening. I know it's only 2 people, but we appreciate you. And we really enjoy doing this, and we would love questions. So sorry for going a little bit over time. But that's it.
Hey guys, this is definitely Tom Singer from Northern Grumman. I want to say you did a good job. One thing that I'd like to see that would kind of make this part of the presentation go a little bit smoother is having slide numbers on your slides. But that said, the presentation is very well put together. The manufacturing technique for your body, you're going to mill the plates out of thick plate material to like cut in stiffeners and whatnot, correct?
That's correct, yes.
Did you look at a overall cost and time comparison to do that versus starting with thin stock and say riveting on some like stiffener, like some channel or angle stiffeners?
I don't believe we looked into that. Part of the reason why we chose to use sort of, I guess, subtractive manufacturing in this case was just to reduce that part count and assembly time. So only having 5 parts for the housing, for example, really sort of reduces all of the points of potential failure and also greatly reduces that assembly time. If you're going in and riveting in a bunch of angle stock or stiffeners, then it's just going to take much longer to assemble.
Yeah, I agree with that. But looking at your manufacturing cost, your manufacturing cost was pretty high, and I imagine a lot of that is coming from the time it's taken to mill out each of those panels. And I'm assuming that's showing up somewhere in like your energy consumption. Not to say that one way is the right way or the other. I know certainly in my line of work, we definitely do the same thing, right? We'll mill things out of thicker stock. For a low production count item, it may kind of bias one way or the other. But that's something that I'd like to see maybe a little more explicit consideration on. Let's see. I think you guys did a really good job sort of detailing your interface with the vehicle. Some of the other teams that I've seen didn't put as much thought, but didn't put as much detail in their presentation about that as you did. But I didn't see a lot of interface with the CubeSat. I know you said that you're gonna kind of like squash that down and have it sprung up against the door. But as far as like lateral constraint, I didn't see any discussion of that.
Right. So so our main concern, at least for us, was the 4000 G shock load that's typical during basically the separation of the stages of the rocket. And yeah, it's correct that we didn't account largely for the lateral loads, but those are mostly structural. So one of the main ones we didn't show, we have it in one of our extra analysis slides, is we did account for a 3G sustains essentially lateral load that we'd expect on the CubeSat. And so that would actually push up against the door even more so. And so we performed an analysis to ensure that essentially our door, even in those worst case conditions where it has the entire weight, times 3 of the CubeSats, it wouldn't cause any yielding of the door. But yeah, I'd agree that we don't have.
Can we back up a sec? Because I'm having maybe a little trouble orienting myself. I'll say the ejection axis of your system, is that oriented axially on a rocket? Is that oriented sort of radially on a rocket?
Yeah, it would be radially. Yeah, sorry, we didn't make that clear.
Okay, so like a vertical acceleration of the rocket is going to induce a strong, like what I would consider for your system, a lateral load on a satellite.
Yeah, correct. Yeah, but we have the shock.
Okay.
That's why we position the shock isolation system there.
Okay.
But yeah, at least for the sustained acceleration. Okay, that's correct. I believe it'd be
I guess I'm interested in like how that satellite is physically attached to or held into your housing. Is it essentially just sort of sitting loose in there and just relying on friction between the door and the satellite, and on the other end the pusher plate and the satellite to kind of hold it in place, or is it locked in some way?
It's locked in laterally using the rails that it sits on. Those are super high tolerance or precision rails to be sure that there's not any slop there. And longitudinally, it's held in by the launch plate contacting stoppers that are adhered to the back facing plate of the housing. So it's really only constrained enough to where it's held in place until it needs to be launched out in that one direction.
Okay. Yeah, everybody's. No, I'm sorry. Go ahead. Good.
Oh, I was just gonna say, I guess one consideration, like you're saying, just a quick, maybe a caution. We could have put some of those, like we have those rubber stoppers on the back to catch that launch plate. We probably could have put some of those on the door, I guess, too, so that way that CubeSat isn't interacting directly with the door. I guess that could have been a safety measure, but we didn't account for that.
Do you know if the CubeSats are designed, how are they designed to be restrained, or are they being designed to accommodate the way that you are proposing that they be restrained? Was there any sort of interface control over that?
Yeah, so the standard, I'm not sure we put the sketch in here, but we have like a representative yellow model that represents the standard CubeSat design specifications for a 12U rail-based CubeSat. So there's standardized dimensions and tolerances for essentially the rails on the sides of the CubeSats and the overall dimensions of the.
So that's,
Yeah.
I mean, that's one part of the interface, but another part of the interface is how the loads get into the satellite, right? I mean, if this thing's being shaken around a little bit, you don't want to load it in a way that it's not designed to be loaded. So somebody's got to control the interface. Either that's you or them or the customer in between you guys who's integrating all this has to define what that interface looks like. And I know other teams have designed doors that, you know, just get shoved out of the way as the CubeSat exits. And Dr. Traum and I had questioned in one of the other presentations, like, is that who's controlling? Who says that's okay to do? And I know you guys are swinging the door open ahead of the satellite, but you know, the door is still part of what's holding the satellite in place. And who is it that says, yeah, that's an okay thing to do on any given CubeSat?
Mm-hmm. Yeah, well, when we interface with our partner aerospace group, they did give us essentially requirements in terms of the shock isolation. But yeah, we didn't actually draft any specific requirements for how the door interface. So yeah, I see your point there.
Okay, yeah, definitely the interface between your container and their satellite should be pinned down. And you know, not to say that you know, anybody in particular is responsible for doing that, but somebody is responsible for doing that. So so I'd recommend considering that. What else do I have? Your I guess your like Swiss cheese rubber deal that you've got sitting, where is that physically located on your structure? Here, can you orient me? Like, is that underneath the like the lateral where, you know, it's sort of the axial load on the rocket is
Yeah, correct. Yeah, so the
okay, yeah.
Yeah, correct. Yeah, each of those
Okay.
rubber isolators is the exact same part.
Okay.
And yeah,
So the thing that maybe confuses me a little bit about this is you've got a lot of rubber under not stiff part of your structure, right? So it's the part in the middle of a panel is not going to be particularly effective in resisting any or damping any sort of motion because it's not going to be loaded. Does that make sense?
Yeah, that makes sense. We did
Yeah.
consider adding ribs along the bottom of that to geometrically increase the stiffness of the centers of the bottom panel there. The rails sort of, oh, go ahead.
Yeah, I mean, yeah, I think you were going right down the right path, right? The rails are where the load is going to be introduced. If you were to stiffen the panel of your dispenser, right, you still have to consider what's on the other side of that panel, right? So on your launch vehicle or your whatever stage of the rocket that you're mounted to, if there's nothing behind it on that side, right, then again, the rubber's not going to do you any good no matter how stiff your panel is. So again, interface control, you know, and knowing what you're attaching to is going to be important there. Let's see, what else do I have? The springs that you've got here, the door hinge springs, and then also the ejection springs. I think you mentioned those were stainless steel.
Yes.
Do you have any concerns about cold welding in space with stainless steel?
I had a feeling you're going to ask about that.
Yeah.
So there is a small clearance between the strip of the constant force spring and the side of the CSD. Additionally, that's not fully constrained against that surface, so it is sort of free to move around slightly.
All right, so that's a stainless steel on aluminum housing, though, right? So that's probably not a cold weld concern.
No.
But as that spring rolls up, right, now you're going to have stainless steel on stainless steel, which is potentially a problem. I guess, is this intended to be reusable at all?
So at least for the NASA Space Launch System that our aerospace groups requested that we make this compatible with, that one essentially for its lunar orbit, this thing just essentially is disposed of in space. So in that case, it wouldn't be reusable.
So one and done. So as that thing rolls up, if it happens to attach itself to itself, you don't care.
Yeah, correct.
What about?
We also didn't really have to worry about the
Yeah.
considerations of the.
What about the door spring?
I don't think that's something that we thought to consider, unfortunately.
Yeah, it might, and I don't have a lot of experience with the space environment or with springs, and certainly not with springs in the space environment. But I know that some types of stainless steel can be susceptible to cold welding, and if you've got a torsion spring like that where you don't have any clearance between your coils, that might be something that could pose a problem. I think a material like A286 could solve that for you, but I'm not necessarily smart enough to say. Let's see, a couple other things. I wrote down a lot. Dr. Chom, if you want to jump in or cut me off because of time or whatever, let me know.
No, you're okay. The next session starts at 3, so you've got 9 minutes.
Oh, okay. Oh man, okay. You had mentioned the door as it springs open, it's going to hit a bumper, right?
Correct.
And I think you characterized the bounciness of that rubber material in some way.
Right. Yeah, the loss coefficient.
Is that something that is temperature dependent?
Yeah, definitely. Yeah, and that's one of the main reasons we recommend testing in this case, because certainly at atmospheric conditions, loss coefficients approaching even 1 essentially, so all the energy lost in one cycle are achievable. But we saw a general absence of data on loss coefficients specifically in the low temperature environment in space. We were able to find that silicon rubber is used as an elastomer in terms of shock isolation in space, but we unfortunately were unable to find data on that. So that is something that we need to probably look more into if this is going to be
okay. Good, you're thinking along those lines. And then I think maybe a couple of slides before this, you'd like shown a plot of your acceleration of your door versus the acceleration of your satellite.
Yes.
What's the blue line here is your door, right?
Yeah. If you could you go back one slide, I can clarify exactly what that's referring to. So that refers to essentially the edge of the door that would impact the CubeSat at any point in time.
Okay. Okay, yeah, I think maybe that answers my question, because I was wondering why it looked like the door was accelerating faster and faster as it got further and further away from zero. And I think the answer to that is that the contact point is sliding up the door. And so that's sort of driving that acceleration. Not that the door itself is
right, exactly.
Maybe a weird thing to call acceleration, but
yeah. Can you go to the next slide, Bree? Yeah, if you look here, this is the actual door angle versus time. That makes it more clear.
Okay.
Yeah.
Okay. Okay. Let's see, what else do I have? I had written down how are you going to load this thing, and then immediately as I was writing that down, I think Bree was talking about, oh, you just put the satellite in, and gravity's enough to hold the extension spring. So that's clever. I like that is sort of a built-in feature of your system. Maybe the question I have is, how is the orientation of this going to be vertical when it's being loaded, or is it possible that there's going to be some sort of integration activity on a launch pad when your container is mounted laterally?
Yeah, so I suppose that's ultimately up to whoever's installing it, but even so, in the case that it's lateral, they would only have to contend with about 30 pounds, which it might require 2 people, I'd imagine, but it should still be safe. And
yeah, even in that case, even if it's only 30 pounds of force or whatever it is, you're still going to have to like force the door closed and like scrape it against the top of the satellite, right? So that's maybe a little concerning. It would be nice to me if you had some sort of retention mechanism that could hold that plate all the way down as you put the satellite in. But if you can guarantee that the integration is the CubeSat's always going to be dropping in vertically, then I think you're okay.
I should note
sorry, go ahead.
Oh, sorry. Yeah, I should note that we have the adjustable stopper for the launch plate. So I suppose one option too is to use the stopper to essentially lock the launch plate all the way back while you're loading it, then put the CubeSat in, close the door, and then readjust the stopper. But yeah, thank you.
Yeah, I think that's a pretty reasonable thing to do. Already built in, doesn't require any change. Let's see, how did you come to the decision to bond the communications box?
That was mostly just an ease of installation, and also since there's such a large surface area on the bottom of that box, there's plenty of bond area between the two surfaces.
Mm-hmm.
Also,
to me,
a lot of
seems
adhesives.
like that's to me it seems like that's something that you'd want to make modular. And if something's bad in the box, be able to take the whole box off and swap it out relatively easily. And bonding kind of precludes being able to do that.
Yeah, no, I definitely agree. In a revised or more final version of this, I definitely hope that the comms housing would be a little more like you could basically get your hands in there and replace parts you need to, or just take the whole thing off. I agree with that. Yeah.
Yeah. And then kind of on the same, communications connections, I think you were talking about a magnetic connection to the satellite.
Yes, sir.
Is there what prevents that from detaching during, say, a launch environment or a staging environment of, I think you were, high G loads.
Yeah. So,
or does it matter?
I don't know if it matters that much. But in a theoretical sense, the launch plate is able to move with the CubeSat's mass during launch and all sort of vibrations, plus that interaction of the two magnets connected to each other. I'd like to do some more testing of it, and it'd have to take some probably some pretty intense like vibrational testing. But I was in theory hoping that would be enough to at least keep it in continuous contact. But you're right, that's probably a good thing to consider.
Yeah, I'd wonder about that. Let's see, what else did I have? The cost breakdown. You'd mentioned that your target cost for this is $500, but that's only a raw material cost.
Yes, that is a raw material cost.
I'll say that's, at least from the groups that I've heard, that's a novel interpretation of the cost requirement. And maybe you guys are right, and maybe some of the other teams missed the mark on that.
Yeah, I forgot to mention as well, for our prototype, we'll be using 6061 aluminum rather than the more expensive 7076.
Okay.
That's why our costs for the raw materials is so much lower.
Yeah. Okay. So you're talking about, all right, so we've got $400 worth of materials and then $3,000 worth of labor to put it together.
Yes.
And I'm looking at your cost breakdown, and it seems like you're talking about 10 assemblers and fabricators spending an hour each, or maybe that, yeah, okay, so 10 hours worth of assembly and fabrication time. What's that being driven by?
That's
And
being
I'll say
driven.
there were other groups that said they, somebody would be able to put one of these together in 3 minutes, and I didn't believe that. I don't know that I believe that there's 10 hours of assembly and fabrication here either. I think it may be somewhere in the middle.
I think it's an overestimation of from using a method that we are encouraged to use in our class. But if we could just like time ourselves assembling the prototype, I think we would have a better estimate to the numbers here.
Okay. Yeah, I think that's overshooting, and that's not even counting. You've broken out machining time separately. Apparently you've got stuff that's being cast in this, which I'm not exactly sure what in your design is being cast. And then you've got like 6 different engineers. Yeah, I guess I'm wondering where all of this is coming into play.
This is just like a theoretical breakdown of like how much the labor costs would like we would incur, and the different engineers, I could go into a little bit of detail about that. For like the mechanical engineers, it's just like they're supervising like the build process. The electrical engineer was for the communication system and just talking about the communications system. And then the aerospace engineer was our interface for the technical interchange meeting, where they told us their requirements and we would just be relaying information through that one person with the aerospace team.
Okay.